In this paper, we present a practical, importance-driven method for GPU-based final gathering. Our method is simple and fast, providing high-quality rendering at near interactive rates. Our algorithm is based on final gathering from a point cloud representing directly illuminated scene geometry. Our main contribution is an importance-driven algorithm that efficiently projects the points to each shading pixel's microbuffer, which stores the occluded radiance field. To start, we sampled the scene surfaces at many points using a Poisson disk sampling algorithm. We then partition the points into spatial clusters, each containing the same number of points. For a given shading pixel, we estimate the importance value of each cluster by drawing random points from the cluster. Finally, we importance sample the clusters and project the selected points to the shading pixel's microbuffer. We compute the projection splat size based on the importance values. This eliminates the need for hole filling in the microbuffers. Details can be found in the paper. Here we show several examples of the microbuffers that we compute. We compare microbuffers generated with a brute force projection of all points, our importance-driven projection, and a purely random projection. Here we compare our adaptive splatting algorithm with uniform splatting using splat sizes of 1, 2, and 3 pixels. We also propose an image space adaptive sampling method. It combines adaptive image subdivision with joint bilateral upsampling to robustly preserve fine details. Since our approach is based on point sampling, we can easily enable glossy-to-glossy reflections. Here is an example that shows such effects. This is done by performing a direct lighting calculation at a scene point when it is requested for projection. We can also enable multi-bounce indirect lighting by treating the scene points as shading points and using the same projection algorithm to update the diffuse radiance at each point. Here we compare direct lighting with 1, 2, and 3 bounce indirect lighting. Here we show the Cornell box scene again while the user moves objects and changes material properties. We also allow the user to move objects at runtime. Note that the indirect shadows and illumination changes in keeping with the user's modifications. In addition, we allow interactive changes to the lighting. Here we show the convergence of our algorithm. Note how the adaptive samples quickly capture the edges and areas under indirect shadow. We show one more example, a kitchen scene. In the footnote, we indicate which illumination components are used in the current rendering. This concludes our video demo.